All right. Good afternoon, everybody. I am here with Pete Shadbolt, co-founder and chief science officer, is that what we call it these days?
Yeah.
Of PsiQuantum. So Pete, I dimly recall giving you $50 million to make a quantum computer. Mm-hmm. How is that coming?
Well, I took part ownership of a 1997 Toyota Camry. About 4 or 5 years ago, bees took up home in the trunk, and then I got rid of it. Now I ride my bike to work very happily. But we were extremely gratified to meet you and meet Playgrounds. What feels like an extraordinarily long time ago now, I guess 8 years ago. And we had deranged claims, basically. So myself and my co-founders had been working together for 15 or so years in the university system in the UK. We thought that we knew how to build what is widely viewed as the most profoundly world-changing technology uncovered by humans to date, which is a full-scale, universal, fault-tolerant quantum computer. And we came to Silicon Valley and started telling people that we were going to build one, that we're going to raise $1 billion, that we're going to put superconductors into a commercial semiconductor foundry and build thousands of wafers of quantum chips, that we were going to develop a completely new epitaxial growth process for a new electro-optic material that's the strongest material known to science, that we were going to take the iconic chandeliers that everyone has seen and that are kind of the icon of quantum computing, throw them into the trash and introduce a completely new class of high-power cryogenics with thousands of times more cooling power, scalability, etc. And a long list of other extreme claims. Improve our architecture at a sustained exponential rate for 6 years running, make integrated photonics components that are better than what Intel can make, than what TSMC can make, the best photonic components in the world. You should have thrown us out the building and called a doctor, I think, basically, when you first met us. And it has been, this is the only real job I've ever had. This is my first experience of gainful employment.
It's your second.
Okay, I used to stack compost in a garden center.
Right.
But it's been a profound privilege for which I owe a debt of gratitude to you, Peter, and to Playgrounds, to have been exposed to the thing that Silicon Valley is famous for, which is doing that stuff and working with a team of brave, brilliant, perhaps slightly naive people who are willing to get on and try to do these things, and to see that engine turning over and to see us essentially bulldoze through these problems, make waveguides with the best optical losses of any waveguide that we know of, go and find 2 national particle accelerator facilities and persuade them to let us put hardware into their facilities. The list goes on. Just to see us overcome those challenges over time has been so emboldening, and it's built a team that, from my point of view, is inoculated against hard things. So the first time that we spoke to those engineers and asked them, hey, you need to make a waveguide that's 10 times better than anything that's ever been made before. You need to put superconductors into a commercial semiconductor foundry. People got really scared. And as they progressively knocked down those challenges, it's built an organization of now 400 people who are accustomed to doing those kind of things. And that's been really an amazing privilege for me.
So I remember when I first met you and Jeremy and Pete and Terry, that the diligence process was tricky, right?
Yes.
Because you were making 2 claims. One is that we're going to make it out of silicon photonics,
yep.
Right? There's $1 trillion have gone into the semiconductor industry, but none of those components are good enough. But you plot them on a chart, and your necessary improvements kind of tracked roughly to Moore's law. Mm-hmm. And having just been doing some work on silicon photonics, is like, okay, this seems within the realm of possibility. The harder thing to diligence was that at the time, the photonic architecture that had been proposed in the KLM paper and one of the authors was from University of Queensland, would yield a machine about the size of the Sierra Nevadas.
Mm-hmm.
And the claim was, don't worry about it, like we'll get the software architecture, essentially the software architecture right,
Yep.
and we'll improve that at exponential rates as well, which was a much larger leap of faith in investing in something that was manufacturable using semiconductors. And bless your heart, in the intervening years, you've tracked these insane improvements in architecture. So how were those dynamics? Did you really believe it when you when you sold it to me? But B, how did that happen?
Yeah, so first of all, I'm lucky to work with people who've been working on this much longer than I have. So my co-founders, Terry and Mark, had already been, and Jeremy had already been on this for a decade. So Jeremy made the first 2-qubit gate for photons in Brisbane, in Australia 20 plus years ago. And then Terry has been thinking about architectures for optical quantum computing since that KLM paper in 2001. The machinery is the same machinery that has brought us this giant wave of interest in machine learning, which is that people knew that neural nets were a good idea decades ago, but they were dismissed as inefficient and impractical. They were only good for toy demonstrations for a long time. And of course, AI went through multiple winters. All the while, strange, deeply mathematically oriented people were chipping away at the resources required to implement machine learning on real hardware. And they brought down the resources required through things like attention and transformers and so on, which, by the way, LinkedIn is the best place if you want to learn about attention and transformers and architectures for machine learning these days. LinkedIn is the place to read about it. But they've brought that down by many, many, many orders of magnitude. And that finally got good enough that you could run it coincidentally on hardware that was built for something else, on gaming GPUs. And we have very much the same machinery, I think, happening in quantum computing, where since that 2001 paper, as you say, we've exponentially reduced the resources required for these architectures by 5x and 10x and 3x and 2x, and compounded improvements like that over 20 years of work now. And simultaneously, silicon photonics, which was originally developed for data center networking applications, and of course, there's a lot of amazing silicon photonics work going on here at Playground. If we'd started 10 years earlier, it wouldn't have been good enough, and it wouldn't have been mature enough. But it just got to the point of maturity where, with a lot of grind from our team and a lot of collaboration with partners like Global Foundries, we knew we could get that to the point of being good enough. And so, a lot of things had to come together. As far as the team, the team that does that architectural work, again, just like machine learning, that's an extremely academic, mathematically oriented, elite team of young people. And it's been amazing to see how they have stepped up to the mark of not behaving like a research group, not behaving like a university team, treating this as a serious, hardcore engineering activity with a deterministic roadmap. And actually, they took quite a lot of inspiration from TikTok at Intel. So they really run a 6-month cadence of oscillating between innovation and execution. And that, I don't know whether that's a magic recipe or not, but it served them actually very well. And it's been amazing to see just how straight that line is as they bring down those resources. So I'm really proud of that team.
Yeah, no, it's extraordinary for those kinds of advances in classical computing, in improvements in architecture, sort of stopped 50 years ago. And we've seen it not only in the core architecture and your fault tolerance architecture, but in the applications or in the algorithms that run on top. And I don't know whether you know, Phasecraft published a good result today, and that doesn't seem to be slowing down. That seems to be in the first derivative seems pretty strong still.
Yep.
And so some of the long-term applications seem to be coming towards the scale of your first machine, things that we thought would be many machines away.
Yep.
So that's an incredibly exciting, unexpected windfall. So one other claim that you guys made early on is that you need 1 million qubits, and don't even bother unless you have a process that can get you there.
Yep.
And so it was entirely through a manufacturing lens. And it didn't require, quasi-particles that may or may not exist, but well understood physics in a domain that was manufacturable. And I think what was extraordinary is the relationship with Global Foundries, that they had the patience to deal with a bunch of crazy people in a startup and took them seriously about developing that process. Do you want to comment on what that journey was like?
Yeah, so this has been Jeremy's obsession for 20 plus years. Jensen, of course, end of last year, famously trashed the stocks of some SPACed public quantum computing companies with an offhand comment that quantum computing is 20 years away. And I'd say he's probably right on average. When you think about quantum computing, you think about science fiction stuff, atoms floating around in free space being shot with lasers, and diamond and atomic scale fabrication and millikelvin temperatures, and it feels like a pretty alien technology. I said to Jensen on stage last week at GTC that I thought the other piece of his quote was the piece that was more interesting and that went missing. If you look at what he actually said, he said, today people have about 100 qubits. Google has a very impressive system which can actually do error correction exactly the way that error correction was supposed to happen, and it can do that with 100 qubits. And that's their chandelier that they love to show in photographs. But you need 1 million qubits. So first of all, thanks, Jensen, for agreeing with what we've been saying to great unpopularity, right, for the last 8 years. In quantum computing, there's an enormous amount of wishful thinking. There's a desperate hope that you can make the machine useful before it is actually useful. And we were really founded on the slightly depressing and aggressive positioning that you better not underestimate the challenge. You have to actually understand that you need a very large system to get this thing built. So first of all, thanks to Jensen for recognizing that. And then he said, look, that's a 5 orders of magnitude scale up, whatever, 4 or 5 orders of magnitude scale up relative to where we are today. The implication being that's a 20-year journey for human beings. And I said to him, look, Jensen, I understand why you feel that way, but you yourself have the counterpoint, which is that the XAI supercomputer built the Colossus machine, Elon Musk and XAI and co., that's a 100,000 GPU cluster that was built famously in 112 days. And I didn't say this, but Jensen likes to say it's 19 days, which gives you a 5x error bar on his timelines. But how is this possible? How can we scale up by 100,000x in 112 days? The answer is by fully leveraging the $1 trillion in 50 years that has gone into the miracle of the semiconductor industry. The fact that you can go and build hundreds of thousands of cell phones with billions of transistors that do 1 billion things a second, that is the leverage that we've always believed in as the key to getting to useful quantum computers much faster than is conventionally anticipated. And that was our obsession from the beginning, that we had to be in a real commercial tier 1 semiconductor foundry. That would give us the volume, and it would also give us the extreme process control that leads to extremely high device performance. But that felt pretty scary, right? Like, these fabs are not interested in the fact that we do awesome, super exciting, weird science fiction quantum computing stuff. They're building chips for cars and laptops and military applications and whatever, and they're building tens of thousands of wafers, and they don't want any nonsense in their fab. And it was really a pretty daunting process. We went and saw TSMC in that process. We saw a couple of other fabs who might have been capable of doing it. And we picked GF really purely on their technical merit. So given the current climate, you would be forgiven for imagining that we picked them purely because they're in the United States. It's actually not the case. They really had the best silicon photonics at the time. And so then we started on this journey of trying to put quantum devices into a silicon photonics process. So this wafer here, this is made at Global Foundries. That's how pretty much all of our chips start out. We make thousands of wafers like this now. We've been doing that for 5 years. This is a 35-layer, 900-step manufacturing process. So there are 35 layers of stuff on this wafer, including a full silicon photonics flow, silicon nitride, beam splitters, ring resonators, things for manipulating single photons. And then there are also superconducting single photon detectors on this wafer that can detect single particles of light with near 100% efficiency. In the workshop here, there's also wafers with barium titanate integrated into that wafer, which is the strongest electro-optic material known to science. To do this, we had to put 10 new mainframes into the fab. So a mainframe is like the semiconductor manufacturing tool that processes these wafers. And it's about, I don't know, half the size of this stage. It's a pickup truck-sized, multi-million-dollar tool containing boiling sulfuric acid, robotic arms, ion beams. You know, it's an alien piece of technology. And it's still actually really blows my mind that they let us do that. I think, you know, it's a testament actually to their team and their willingness to trust us. And it's also a testament to the engineers in the PsiQuantum team who proved again and again that they were worthy of access to this hallowed ground and to this like extraordinarily rare resource. And of course, we've pushed the performance of the GlobalFoundries silicon photonics process in that partnership. And we've also done, you know, productive things together. So for instance, we have now a total of more than $30 million in contract with the Air Force Research Lab in Rome, New York. We're making chips for the Air Force in that context, and various other activities going on. But it's just been an amazing partnership. We now get 95% functional yield on these wafers, and we just make insanely good devices. All of the components that we need for a 1 million qubit quantum computer, all with beyond state-of-the-art performance and fully integrated into a high-volume manufacturing flow. This has been the dream for us. And this now puts us in a position where our focus is shifting from getting the materials ready, getting the devices ready, and shifting much more towards building the big systems that are now coming online at the Stanford Linear Accelerator in the UK, and also soon in Australia and Chicago.
Yeah, I want to talk about what the roadmap is between now and when there are big machines. But just on the barium titanate, that didn't exist.
Yeah.
There was no such thing as a barium titanate optical switch.
Yeah.
Right. Lithium. I think lithium niobate was state of the art back then.
Yeah.
Where did GlobalFoundries get that technology from, and who makes those films?
Yeah. So. I have a favorite ex-Twitter user who's just completely obsessed with advanced photonics, and he's a Stanford student. He came to the lab to see these films the other day, and he left and immediately posted that he wished he'd licked the wafer because he couldn't believe. He was asking, what does BTO taste like? Because I can't believe that's real. He's obviously worked on similar problems.
It's good to have hobbies. Right?
But we're not going to let him do that. Although I do actually happen to have the fingerprint of multiple heads of state on this wafer, if there are any intelligence community people in the room who like that. But yeah, so this was yet another kind of like call the hospital, these people have lost their minds kind of moment. And this was much later in the game. So when we raised our Series D fundraise that was led by BlackRock, we told them that the hardest problem for us was to develop a completely new optical switching material and integrate that into a manufacturing flow at GF. And that really was something that tested the bravery of people inside the company. I suspect it might have tested your bravery somewhat, Peter.
I wasn't doing the hard work, so it was.
and various others. In that, you know, we had to build a completely new manufacturing tool. So a brand new epitaxial growth process. That tool is in San Jose. It's half an hour's drive from here. That is probably about the size of this stage. It's the biggest molecular beam epitaxy tool in the world. It has molten titanium in it at a few thousand degrees Celsius. It also has liquid helium in it, exposed to the same vacuum chamber, and it grows basically perfect wafers of the strongest electro-optic material in the world. And that's not just in an R&D context, right? We then have to be able to take wafers out of that tool, load them into a FOUP, FedEx that to global foundries, and integrate that into their flow without poisoning a 300,000 square foot tier one semiconductor foundry. So we have to be able to do that essentially at the highest level of maturity that exists in semiconductor manufacturing. And we laid out a plan of 3 years to do that. We wanted to get films in 21. We wanted to do lithography in 22 and integration in 23. And this was the critical capability for the company. The shipping company managed to drop the main vacuum chamber in the Alameda Bay and crack it. And so we were a little bit late on films. We were on time with lithography, and we were ahead of schedule twice over with integration. That was a lot of work by the team, but yeah, it's been an amazing success story for the company. We're the only supplier of that material. We're the only people in the world who can make 300 millimeter wafers of that stuff. And we get, after publishing this Nature paper, which is our first hardware paper in 8 years, a few months ago, we heard that the Global Foundries team got like 15 calls from customers saying how can they get hold of this stuff. And that's mostly for classical applications, for optical networking, for data centers, for switching in AI supercomputers. And yeah, it's a joy to work at a company that is doing beyond state-of-the-art development and execution, from the angstrom to the nanometer to the micron to the centimeter, and now all the way up to the kilometer scale. And there's a lot of amazing technology coming out as a byproduct of that development.
Yeah, when the figure of merit is switching or detecting individual photons,
yeah,
the sort of bright light classical applications, you have a lot of headroom, right? And so just as the waste heat product of building a quantum computer, you've developed the most sophisticated silicon photonics process and optical switches on the planet.
And it's underrated to be forced to do hard things. We had no choice, like that was kind of the holy grail of materials for optical switching. And I think other people understandably went for more modest approaches. That was the only thing that would ever work for us. And so we were forced to take that risk. And we are a startup. We do very short learning cycle, chaotic, multi-path kind of development on some pieces of our work, of course. But it's quite interesting that we're also a startup that makes things in a commercial semiconductor foundry. And so there is another piece of our organization that actually has to be uncharacteristically rigorous, actually quite slow moving, very deliberate. And with the BTO, with this material, we really had to adopt that kind of mode of operation on something that was viewed as a crazy risk, but that has really, really paid off for us, yeah.
And so I think 2025 is Year of Quantum. And last year, of course, end of last year, Google announced Willow, which I think you'd agree is probably the best quantum computer on the planet at the moment.
It's the best quantum computer, yeah.
It's 10,000 times smaller than the machines you're constructing. But since then, we saw the Majorana 1, we saw the Ocelot, we saw a number of announcements of breakthroughs.
Yep.
And how do we know the one you're building is the one that's going to get to scale and actually work, when there are all these other modalities that are going to eclipse you or solve some mysterious set of problems with a breakthrough that is otherwise unimagined?
Yeah, so let me comment on quantum computing, and then on breakthroughs, and then why we're the best. So I think those are the topics you touched on. So just on quantum computing, yes, you've seen lots of news and hype and breakthroughs and disasters and victories and failures and everything else. And to me, that is a byproduct of the fundamental reality, which is that quantum computing is the final frontier in this sequence of human beings coming up with categorically faster and new ways of computing. And it's sitting there as unexplored territory. There are problems in chemistry, material science, drug discovery, fuels, catalysts, whatever. Peter, you spoke so nicely about this earlier, that we will never solve until we build this machine. And so it has a profound inevitability to it, where you got to do it. And if you'll forgive me telling the anecdote, this was 10, 12 years ago. I was with the Microsoft group, actually, with Krista Savore, who leads that effort in Seattle, and we were out for dinner with that Microsoft quantum computing team. Steve Ballmer came around the corner, and Steve Ballmer, of course, is a big presence in any room, and we said, wow, here's Steve. And Krista is the strongest cocktail orderer of anyone I've ever met. I'm the opposite. I'm like terrible at ordering cocktails, but her precision with ordering a cocktail is unreal. She's sitting there with this thing. And Steve says, hey, Krista. She says, hey, Steve, what are you up to? And Krista says, quantum computing. Steve says, you gotta do it. And then he left. And that still rings in my ears, that if you don't do it, like if you don't build this machine, in 1,000 years, human beings will be sitting somewhere saying, if only we had a quantum computer, then we could design this drug, we could solve this materials problem, we could design this fuel, whatever it is. And so that is the context in which it's still a news item. Thousands of our best scientists and engineers are still devoting their entire life trying to realize this technology, and it just keeps on having this insane gravitational pull. And then as far as breakthroughs, yes, in quantum computing, the news is always about breakthroughs. Google has a breakthrough, Microsoft has a breakthrough, blah, blah, blah. I think that's a journalistic failing, basically, in that breakthroughs are cool, but think about legendary companies. Think about Intel, TSMC, ASML, SpaceX, NVIDIA, Waymo. Waymo is actually my favorite example, even though I know it pains you, Pierre. But all of these companies, like, did they really get there through breakthroughs? And there's many people in this room who can correct me, and I'm going out on a limb, but I'm pretty sure they did not become legendary companies via breakthroughs. I'm pretty sure that those organizations became legendary companies through very, very dogged, sustained, extremely hard, extremely technically involved work, and getting to a level of maturity that is worlds away from the breakthroughs where they started in a university research lab in an R&D environment. And that's really the sort of culture and attitude that we've tried to engender at PsiQuantum from the beginning. We have breakthroughs, we have amazing scientists in our team, but the figure of merit is that you can turn that into something that you can build at scale, that is reliable, that you can build in volume, that fits into a real machine, and that is just as hard, if not harder, basically. And so I think, breakthroughs are the beginning of a journey, not the end, is really the simple way to put it. When you see a news article about a breakthrough in quantum computing, sometimes it's easy to fall into the trap of feeling like that means that an engineer at Google or Microsoft or something, they had an amazing night in the lab, at 2 o'clock in the morning they made a breakthrough, and now the quantum computer is suddenly going to appear the following morning and start stealing all of our Bitcoin. And of course, nothing could be further from the truth. Now, you are on a decade-long journey to turn that into something real. We had our breakthrough 20 years ago when we did the first 2-qubit gate in Brisbane, and it's been a little tiring ever since.
Yep. So one other phenomena that's come to the fore in the years since you began was that of AI. And some very thoughtful, very clever people, if you ask them what their fondest hope for AI is, they inventoried the quantum scenarios that you talked about.
Yeah.
So give us a sense of how you think about AI broadly and the relationship between quantum and AI in the future.
Yeah, so happy to announce today that we're announcing our new product, which is called Gen QAI. So it's like a language model that runs on no, this is nonsense. And so you should not expect that you are going to use a quantum computer to accelerate conventional AI workloads. It sounds great. You can make word salad with quantum and AI and post that on LinkedIn, and that's not real. What is very real is that there are fundamental limits in terms of how far you should expect to be able to go in simulating molecules, reactions, materials, chemistry, physics, etc., using any kind of conventional computer, including AI supercomputers. And so, we're going to build bigger AI systems. 3 Mile Island is going to turn back on. One day, Microsoft will recommit to multi-gigawatt systems and so on and so on. But that brute force approach is running into a very, very steep wall. And there are huge swathes of value in chemistry, materials, etc., where you should only expect to be able to access that with a quantum computer. And the serious way in which you can make word salad with AI and quantum is that you really can expect that quantum computers will be used to generate precise data from first principles, and that data will then be used to train conventional machine learning models, which we can use for drug discovery, materials science, battery chemistry, whatever. And so the way I think about this is that machine learning has been very successful in making approximations that are learned from data, whereas what quantum computers are good at is a first principles exact calculation from the ground up. And so I think these are very complementary capabilities. And we know that these AI systems are going to run into walls in terms of availability of data, and hopefully we're going to be there to save them when that time comes.
So before you build the machines, you've been engaging with partners on how you commercialize this thing. Mm-hmm. So what's it for, and what do you do between now and when you have the big machines?
Yeah, so if you think about the Fortune 100, I don't know what you guys visualize when I say Fortune 100. I typed this into an AI image generator the other day. If you just get Midjourney or something and type Fortune 100, it shows you men in suits shaking hands with each other. So that's what the Fortune 100 is according to AI. You guys know car companies, materials companies, energy companies, pharmaceuticals, semiconductors, defense. So many of these industries sit on a microscopic foundation of chemistry, physics, and math, whether it is the drug molecule, the fuel, the catalyst, the pharmaceutical, the semiconductor manufacturing process, whatever. And those molecules, reactions, materials are all, as you said, ripe for reinvention, overdue for reinvention, looking long in the tooth. And so those are the companies who come and work with us. We work with a long list of Fortune 500 car companies, materials companies, whatever, all the usual suspects. And they're coming to us understanding that we don't have a 1 million qubit quantum computer today. We don't have a useful system that they can run code on. But we're going to have one very soon. And they want to prepare for the existence of that machine. They don't want to be taken by surprise by one of their competitors having suddenly categorically new level of precision and predictability and speed of innovation on drug discovery or battery chemistry or whatever. And so, yeah, those are the guys that we work with today. We're very grateful for those partnerships. Some of those are 6 months old. Some of them are nearly 6 years old. And we're continuing to bring those guys along. And, of course, we learn a lot from them, talking to their engineers, talking to their teams, and understanding what it is they want to solve with those systems when they first turn on. And there's just one maybe small thing to add here, which is that there's a lazy sales pitch for quantum computing, which is that it's all about mass adoption, it's all about user friendliness, it's all about getting tens of thousands of students to learn to program the quantum computer. And it sounds good, but it's honestly dishonest in that, a quantum computer is always going to be a pretty technically demanding piece of equipment to operate. And this is, again, by analogy with ASML, SpaceX, NVIDIA. Like, how many people have ever actually, prepared a tape out at Intel or TSMC or Global Foundries? How many people?
Well, that
I
guy.
mean, there are quite a few people in this room, but this is a disproportionate group. You know, how many people actually on planet Earth design a payload that goes onto a SpaceX rocket? How many people actually
How many people have
run?
been on a SpaceX
I mean,
rocket? I think
unfortunately, this whole story doesn't work with this audience. But you understand the point, which is that, of course, we actually work really hard to have user-friendly software. We have a 25-person software team. It's all Python. It's beautifully documented. It's actually really awesome. But it is not an obstacle to growth and to us becoming a legendary company, that this is a technically involved machine to operate, and that this is a small group of people who directly interface with the technology. Just like those examples, of course, 99.9% of people never get anywhere near a fab, but they've all got cell phones in their pockets that wouldn't exist without that fab. And we really hope that quantum computing functions in the same way, that the second and third order products of the technology, the drugs, the fuels, the materials, whatever, that those end up being used, hopefully by people who couldn't care less that that was designed on a quantum computer and wouldn't have ever existed without a quantum computer. I'll be delighted if we get to that point.
Great. So let's talk about getting them built.
Yep.
So you've got a series of partnerships with national labs, with DARPA on the utility scale quantum computing program, with the Australian government, who gave you 940 million Australian, which is still a non-trivial amount of money in US dollars. The city of Chicago and the state of Illinois to construct 2 of these million qubit machines. You've also got partnerships with Daresbury in the UK. How does what does the program look like between now and when those 2 big machines are commissioned?
Yeah, so I think the context for that is that, of course, we're all painfully aware, like in the last few years, governments have started to understand technologies like this as sovereign strategic capability. And I think semiconductor foundries were the first technology to really cement that idea in people's heads, that some of the advanced technologies on which our society is built have the physical property that they concentrate power, that you end up with a billion-dollar machine that is rooted into the ground where there are only 5 or whatever of those systems on the planet, and the location of those systems really matters strategically, geopolitically, etc. So that's the context, I think, in which we've been working, especially with Australia and with the Illinois government. And you asked earlier about the competitive positioning, and there's endless competitive positioning in quantum computing. It's like the early days of the microelectronics industry. I wasn't there for it, but that's what I've been led to believe, which is that, as far as I can tell, it's actually an anomaly today that we all agree basically on the silicon transistor, and we all sit on that same foundation. It used to be that people were building bubble memories and delay line memories and buckets of mercury and 15 different things, and all arguing vociferously in favor of their own technology. Quantum computing is like that. It's absolutely violent, mudslinging, endless arguing over photons versus ions versus superconducting qubits. And of course, there's legitimacy to those very nerdy technical arguments, but there is a completely separate set of necessary but not sufficient criteria that completely go missing, in my opinion, in a lot of this discussion, which is, first of all, have you quit the university? First of all, you're almost certain a university professor if you're a founder of a quantum computing company. Have you exited the university fully? Okay, with that given, now, can you tell me who your production fab is? Can you tell me that you've made thousands of wafers in that fab? Can you tell me how you're going to cool the system at scale and who's building that cooling system for you? Can you tell me who your contract manufacturer is, who your OSAT is, what your supply chain looks like? And most of all, can you tell me where you are going to build this machine? In almost every case, this is a data center like 100,000 square foot plus building scale machine. And so tell me where it's going to be built. And also, have you been through a deep government diligence process? has a government provided hundreds of millions of dollars of non-dilutive capital for you to build that system? If the answer to any of those questions is no, that's fine. Like, you may have a very compelling technology, but you are very far from even beginning to build a useful machine. And that is, again, necessary but not sufficient. There are lots of other technical questions to address, and DARPA has been an amazing partner in taking a very skeptical view of our claims and grilling us for 4 years now on those claims. So they started from the assumption that quantum computers will be commercially useless and that nobody knows how to build any useful quantum computer anytime soon. They built a red team whose success criteria was the number of bad ideas that they could destroy in quantum computing. And they told that team to attempt to show that what we're doing doesn't work and isn't worth any money. That was originally a 10-person red team. It grew to a 50-person red team from the national labs, from the universities, from DARPA, et cetera. And I'm super proud of the PsiQuantum team, who've basically stood up to that onslaught for 4 years. They've now graduated to the final phase of that activity. That DARPA quantum computing activity is consolidating into a single program. It's relocating to the Chicago site with us, where we're the anchor tenant. It's growing to 200 people from that red team, and it's robustified our efforts a lot. But yeah, if you can't answer those questions, you're only getting started, and I'm very excited that we now can answer those questions. We're building our first system on a site that's just outside Brisbane Airport in Australia. We're breaking ground there in the next few months. We're under contract with the guys who are going to build the cryogenic system there. And then the same in Chicago, where we are privileged to be the anchor tenant of a $500 million campus endorsed by Governor Pritzker, Mayor of Chicago, and many other people. That's on the former US Steel site. So that is a site on the south side of Chicago where they used to make 1 million tons of steel a year. There are 2 absolutely giant, roughly 1 million square foot pads of concrete on the lakeside there, and we'll be breaking ground on that site also in the next few months.
And so I notice over your shoulder, Kendra, pointing at a wrist, which I think means like we're running along. And I could talk, or the next thing, yeah, it's good. I could talk to you about this, as I have many times for many hours, but I want to ask one more question, and that is, okay, these machines are built, they're operating, they're running workloads.
Yeah.
What do you do next?
Build better ones.
All right. Pete Shadbolt, everybody. Thanks so much. You want JP Wafer? So.